The manipulation of the form of linear objects is a challenging task for a robotic system due to their unpredictable configuration, high-dimensional state space, and complex nonlinear dynamics. The shape control tasks involves the manipulation of soft DLO with a sequence of pick-and-place actions, where the deformation of the DLO is held in place by the friction of the surface. With this work, we contribute with a manipulation framework targeting the model-based shape control task of DLOs with a focus on adaptation of the model parameters. Two different types of DLO models are exploited, specifically a physics-based analytical model and a neural network-based model. And the method consists of two phases. In the training phase, the analytical model is used for the generation of trained dataset, which is employed to optimize the weights of the neural network model. In the online phase, the neural network model is utilized for the shape control task since it has two major advantages, differentiability and fast inference speed. For the training phase, the analytical model is randomly perturbed to simulate pick-and-place actions, and this way, a trained dataset of interactions is generated. The neural network model takes as input the current DLO shape, the actions, and several model parameters. In the online phase, only the neural network model is employed. By changing the input and output of the model, it's possible to accomplish two different objectives, namely action estimation and parameter estimation. And they are accomplished employing the same neural network model with a gradient-based procedure. The experiments involve two different surfaces, a cloth and a carbon, and three rows, white, black, and red. 4 target shapes are considered, and the objective is the simultaneous execution of a shape control task toward the target goal while estimating the model parameters. Here are the results on the S target shape. It's possible to observe how different actions are executed for each DLO surface pair. The results highlight how less than 12 manipulations are required to reach the goal, and in addition, on the cloth surface, similar bending parameters are estimated for the same rope regardless of the target shape. Comparing the online estimation with the mid-range and best parameters, it's possible to see that few iterations are enough to reach the best scenario performance. And finally, the method was tested with the state-of-the-art network and architectures, highlighting how the model with conditioning of parameters is architecture agnostic. The adaptation of the input model parameters performs better than the direct adjustments of the model weights.